Hi everyone, and thank you so much for having me in your classroom today. My name is Marina McNeil, and I'm from the University of Utah, and today I'll be talking about metallurgical engineering and my department, which is material science and engineering. Now, I graduated in metallurgical engineering a few years back, and I'm extremely passionate about it, and I hope you'll learn something new from this presentation today. Please make sure that you put your cell phones away and you're participating and being an active audience. I do have a bunch of goodies that I've given to your teacher for them to hand out to you if you do participate or answer questions. So anyways, let's please begin. So let's begin. What is metallurgical engineering? What does it sound like? Metallurgical, I know, can be a bit of an intimidating word. I know when I told my grandma I was majoring in metallurgical engineering, she didn't quite know what that was or believe me if that was an actual engineering major. So can anybody give me a guess of what they think metallurgical sounds like? You can pause this video here. Now, I'd imagine probably one of you said engineering metals, and that's correct. We work with metals every single day. Metals are all around us. We have them in our currency, in our suitcases, in our cell phones, in our computers, in our transportation, bicycles. I mean, it's even in our toothpaste. It's pretty crazy, but metals are very applicable to life. So next question, what is a metal? You guys have probably taken some sort of science class, so just give me what you think a metal is. And you can pause the video here too. So you probably gave some different properties of a metal. We've got hard, shiny, opaque, electrically conductive, thermally conductive, and these properties aren't true for all metals, but they are true for some of them. Something that I find pretty interesting is 80% of the periodic table is made out of metals. That's a lot of our elements on Earth that have metals in them or are a compound with metals. Now here's another question. Hopefully these are getting a little easier. Where do we get metals? You can pause the video now again. So probably one of you might have said that we get it from the ground, or we get it from the earth, or if one of you were very adventurous, you may have said that we get it from an ore. So we can also get metals naturally. We have several over here on the right side of the screen, which I'm not sure why, but I can't get the cursor to show up. So on the right side of the screen, you'll see a man digging for gold. So gold is extremely dense, so it'll settle towards the bottom of the pan when you are gold mining. There's natural copper. Copper is not super common to find naturally, and usually if we find natural copper, we'll just extract it with the rest of the copper that is with the other compounds of gangue material. And then there's also iron. Now iron has an asterisk next to it, and that's because iron, when it's found in its natural form, is generally from a meteorite. So this dagger right on the right side of this screen was actually found in King Tut's tomb, and it was carbon dated to be 1,000 years older than when we started extracting iron. And that's because that dagger was made out of a meteorite. Now, as I said earlier, you guys might have said that you get metals from an ore. Now, an ore is a rock with a high concentration of metal. It's generally just a simple rock, and then it's got some amount of metal in it. So right here, I have a ore, or a rock, with a high concentration of copper. So right here, you can see that turquoise coloring, and that is our copper metal. So there's an ore. So metals are extremely valuable because of their physical properties and uses. We've got density, electrical and thermal conductivity, melting temperature, ductility, magnetic properties, hardness, specific heat capacity, and many more. As I said earlier, these aren't true for all metals, but they are true for a lot of metals. Now, can anybody tell me what density is? You can pause this video again. Now, one of you probably said that density, you may have said the formula, so it's mass divided by volume. I actually learned in middle school that density equals heart, so you have the M on the top and then the V on the bottom. And density is just how close the atoms are packed. We've got 4 different types of metals right here. I've got 1 pound of magnesium. Let's see. 1 pound of magnesium, 1 pound of aluminum, 1 pound of tungsten, and 1 pound of copper. Now, although all of these have the same mass, they have different volumes and they have different densities, as you can see. So we can use the different properties of metals for different applications in our world. Obviously, if you're going to be shipping a rocket to Mars, you're probably not going to want to use purely tungsten because it's extremely dense and it would take a lot of energy. Now this is one of my favorite metals. This is gallium. So gallium is actually a solid at room temperature, but once it's heated up to body temperature, it actually turns to a liquid. So right here we can see that a person is just holding it in their hand and it's a solid and then it turns into a liquid. Now, gallium can actually act as an artificial mercury. It's a lot safer. As you can see, this person is just holding it in their hand. It's very, very safe, and you can mix it with tin. So you can make an alloy of gallium and tin, and it acts as an artificial mercury. They also sometimes use gallium in the sprinklers within buildings. So I'll put a piece of gallium right on top of the sprinkler, and once it turns to a liquid, it will trigger that sprinkler to start releasing water to extinguish the fire. Now here I have bismuth. So bismuth, when you purify it to 100% bismuth, it'll actually be a dull gray color, so kind of like the pole on the bottom of this screen. And as it oxidizes, it'll naturally turn to those colors that you see in the center of the screen. So the green in the center and the pink and the yellow outer edges. And bismuth is also diamagnetic. Now I don't think anybody will be able to get it, but I'll still pause the video and see if anybody can. So diamagnetic means that it repels both north and south poles. So good job if you guys got that one. So can anybody raise their hand and somebody tell me what science is, and then somebody else tell me what engineering is. You can go ahead and pause this video again. So science, we like to say, is the study of the physical world, whereas engineering is applying those sciences to make our modern day technologies even better. So before you started watching this video, you probably weren't too aware of metallurgical engineering. Now there are a lot of different engineering fields. We've got mechanical, civil, chemical, bio, environmental, electrical, computer, nuclear, and the list goes on. Those are the more common engineering degrees. However, metallurgical engineering is pretty amazing and it has a lot of applications to our world. And there's a lot of overlap between the areas. So if you've been considering STEM or different engineering majors, I'd recommend to try metallurgical engineering if you haven't quite decided what type of engineering you specifically want to go into. And if you have decided on a major, maybe you'll decide that metallurgical engineering might be for you. So right here we have mechanical engineering. Mechanical engineering has a strong emphasis in math and physics. Now there's still some overlap between earth sciences. It looks like my little talking bubble cuts off the earth sciences, but that's what's on the right side of this, the little pentagon. So we've got math, physics, earth sciences, biology, and chemistry. Then we have civil. Civil is a bit more well-rounded. We have a bit more of an emphasis on earth sciences and math. Then we have chemical that has a strong emphasis on chemistry, math, and physics. Bio that has a strong emphasis in biology, and then still some overlap with chemistry, mathematics, and physics. Not so much earth sciences. And then we have metallurgical. So metallurgical is pretty well-rounded. It's got chemistry, mathematics, physics, earth sciences, not too much biology. However, if you are interested in biology, there are a lot of different applications that you can use metallurgical engineering for. Some of those are prosthetics, tuberculosis sensors, biomedical sensors, pacemakers. There's a lot of different applications, and I'll talk more about that later in this presentation. So metallurgical engineering is one of the oldest engineering in the world. It's actually been around for thousands and thousands of years. So if you look back on history, there are a lot of wars that we've fought as many world nations. So we've got a lot of different weaponry that are made out of metals. We've got swords, daggers, anvils, trebuchets, catapults, even bullets. All of those have metals in them. Now we also have used metallurgical engineering for a lot of monarch and monarchies, different jewelry and precious metals. You've got crowns, you've got bracelets, necklaces, anything that's got some sort of metal, a lot of pretty decor has metallurgical engineering involved. Now, because of this, a lot of people think metallurgical engineering is a done field. They think we've already mined all the metal we're going to need, and we're going to need to come up with something new. Well, coming up with something new is definitely right. However, metallurgical engineering is not a done field. There are a lot of elements in a lot of those metals. On the periodic table that I mentioned earlier, 80% of the elements were metals. So that's a lot of metals. And a lot of those metals haven't been extracted or purified in large enough quantities for us to use them until the last 100 years or so. So if you think about it, we've got cell phones, we've got computers, we've got electric cars, we've got vehicles, we've got rockets going to the moon. All of those have some sort of metals that have contributed to them. So something that I found interesting, found out, I think it was last week, that in your cell phone, the vibrate mode on your cell phone is actually caused by something called a neodymium. Neodymium is an element. It's one of those transition metals on that second level of the periodic table. And neodymium is a rare earth metal. Now, rare earth doesn't mean that it's necessarily rare. It's quite plentiful. However, it's pretty difficult to extract. Something else that I learned, so anyways, there's neodymium magnets within your phone, and the force between the neodymium magnets is what causes that vibration in your phone. Now, something that I learned last week was aluminum actually used to be considered a precious metal. Aluminum was going to be the cap for the Washington Monument in Washington, D.C. However, in about 1860, they were able to find that aluminum had a new extraction process, and now aluminum is very plentiful to you and I, and actually pretty affordable and cheap. We've got aluminum right here, but before it used to be pretty difficult to extract. So I hope in the future we'll be able to do the same thing with rare earth elements. And because of that, we can use a lot of different materials and different alloys with those metals for our everyday world and our technologies that we use every single day. So let's look at the big picture. Can you guys raise your hands? How many of you guys are sophomores? How many of you are juniors? And how many are seniors? So you probably are starting to think about college or university or where you're going to go after high school. So I wasn't aware of this until after I got into college, but it will definitely be helpful if you are aware of it now. So we kind of have a hierarchy at the university. We have a university level, so that would be University of Utah, Brigham Young University, Utah State University. It's applicable to pretty much every university. Then underneath your university is your college. So as I said, we're the College of Mines and Earth Sciences. We actually have a pretty unique situation where because of metallurgical, we're part of the Mines and Earth Sciences, but we're also part of the College of Engineering. Then underneath your college is your department. So as I said, my department's Material Science and Engineering. And then you have your degree, which my degree is Metallurgical Engineering. All of the different types of engineering would also be a different degree. Now, I'll talk about it more later, but there are different scholarships available in each of those steps in the hierarchy. So when we get to scholarships, I'll talk about how you can apply for each, the degree, the department, the college, and the university scholarships. So our college is actually one of the oldest colleges on campus, but it's also one of the smallest colleges on campus, which is pretty beneficial for us because there's a lot of a connection between the students and the faculty and the students and the students. So it's actually established in the Utah Constitution that there has to be a College of Mines and Earth Sciences at the University of Utah and a degree specifically for metallurgical engineering. So right here we have two of our buildings on the left side of the screen. We have the William Browning building, and then connected to it is the Frederick Albert Sutton building. Now this picture in the middle is the Frederick Albert Sutton building, and inside there are a bunch of different artifacts from the different departments and what they bring to our college and kind of what they've found when they've been out doing research. So there's different ore bodies, there's fossils, there's a dinosaur head that's been like a prototype of it. There's different pictures of what people have seen when they are in their research field. There are a lot of cool artifacts, and in there is also a really nice coffee shop. I really like that building because unlike the library, not a lot of people know about the Frederick Albert Sutton building, and there's a lot of spots to be able to go and study. I'm definitely one of the types of studiers that likes to study alone when it's quiet, so that's really nice. So as I talked about, there's different departments within our college. So the first one I'm going to talk about is the geologists. The geologists are in charge of locating the Earth's resources and studying the Earth's land dynamics. They study prehistoric life and earthquakes, volcanoes. They'll study environmental science, the impact humans are having on the world, and most importantly for us, they locate the Earth's resources. Now, as I mentioned, the human impact, what the geologists are in charge of, I actually went down to Ecuador with some geologists and geophysicists within my college, and I was able to receive upper division course credit, which was really nice because I was able to work in Ecuador studying the effects of residual mining. So residual mining is kind of smaller scale mining. There's not many restrictions with government, and because of that, they put a lot of waste down the waterways, and that can affect the plants, animals, and then the people down there. But I was able to work with many different departments in our college, and we were able to go to Ecuador and then come back and write kind of a document for the Ecuadorian government on how important it is to dispose of the waste properly. But it's an amazing field. Then the geologists give their information to the mining engineers. The mining engineers are in charge of obtaining the Earth's resources. So they'll plan the site, they'll survey the area, they'll design the mine. Right here we actually have, well, with the haul truck picture, you guys can't see where I'm pointing, but the haul truck picture is of a mine. We actually had a slide about 10 years ago at the Bingham Canyon mine, which is just west of here, depending on where you are in the world, where I am right now. And because of the mining engineers and their predictions that they were able to make, they were able to safely evacuate everybody from the mine, and because of that, there weren't any casualties or injuries. Now that's a very fortunate event for Rio Tinto and the Bingham Canyon mine, because the mine runs 24/7, so we were very grateful for the mining engineers. They also work with mineral extraction. So we've got the blasting. Blasting's on the bottom left of this panel. Blasting, I like to think, is kind of like a big fireworks show inside of a mine. So they put extractants inside of the Earth's crust, and then they break it down. So a boulder about the size of this room would be broken down to something a lot more manageable, something like this, or probably around a 12-inch particle size diameter. And then a metallurgical engineer would be in charge of breaking down those materials to even smaller so we can get just that metal. They're also responsible for the environmental impact. So as I was mentioning with Ecuador, water contamination is definitely a problem with mining if we don't do it correctly and we don't follow restrictions. So mining engineers are in charge of following those restrictions, following the EPA standards, and making sure that the water is not contaminated where plants, animals, and people will be living and surviving. And then they're also in charge of reclaiming the land after they're finished using it. So they have to make sure that it's hospitable for plants, animals, and people after we're done getting that material or metal from the earth. So actually something that I found interesting is Daybreak is a bunch of reclaimed land from Rio Tinto. So kind of neat. Then we've got the mining engineers that give their information to the metallurgical engineers. Now there are two types of metallurgical engineers. There's a physical metallurgist and extractive metallurgist. Let's start with the extractive metallurgist. As I said, the extractive metallurgists are in charge of breaking down this material to get just the metal. And then we also have recycling. So if we can use something that's already been mined, we've already extracted that ore, it's going to be a lot easier to reapply to a new technology rather than having to go and mine it again. Then we have the physical metallurgists. So the physical metallurgists are in charge of alloy design. So that's usually when you have a metal and a metal or a metal and a non-metal. They can work with implants, alternative energy production, nanomaterials, and my brother actually went and did physical metallurgy, and he's actually a rocket scientist now. So there's quite a big variety of different careers and different jobs that you can apply metallurgical engineering to. We have other types of engineers within our degree. They convert alloys into new products. And then we also have the atmospheric scientists. Now the atmospheric scientists aren't necessarily an engineer, but they're extremely important because they measure the impact the environment that we're doing to the environment or the environment is having on us. So they'll study the weather, forecasting, model wildfires, and just forecast and predict climate change. So they're extremely important. Sums up our college. As I said, we're actually part of two colleges. So we also have the College of Engineering. The College of Engineering would be material and science engineering, mechanical engineering, civil engineering, biomedical engineering. All of the types of engineering are also in the College of Engineering. So as I said, there are two different types of extractive metallurgy. There's hydrometallurgy and pyrometallurgy. Pyrometallurgy has to do with heat. So on the bottom right of this panel on the left side of the screen, we have a blast furnace. So a pyrometallurgist would work with, or an extractive metallurgist in pyrometallurgy would work with pulverizing this rock to make it very fine particles, and then you would add different chemicals to a solution where the particles that were metal would actually become hydrophobic, float to the top, and then you could skim them off the top, and then you could put them into a blast furnace to further concentrate them. Now, a hydrometallurgy extractive metallurgist would work with diluting acid and by adding water and then dripping the solution onto material that has metal on it. So it would be about a 2-inch particle size or lower, and the solution would be dripped onto the material, and then it would absorb the metal particles and materials, and then you'd be able to plate it onto a cathode and then have sheets of copper that you could send to your client or your customer. Now on the left side of this screen, I have a picture of a gray-brown pit area with blue in the center. Can anybody tell me what that is? You can pause the video right now. So you may have guessed that that is Bingham Canyon Mine. So that is in Utah. It's actually one of the best places to mine copper in the world. So can anybody give me a guess from 0 to 100, or a few of you maybe can guess, what concentration of copper is in the mine if it's the best place to mine copper in the world? You can pause the video. So you might have been pretty surprised. It's around 0.1 to 1% that is our concentration of copper in that mine. Now because of that, we have to do a lot of crushing. So we'd have to break down this material to very small particles for pyrometallurgy. And for hydrometallurgy, we're going to have to get it to about 2-inch particle size and lower. So it's going to take a lot of crushing. It actually takes 4% of the Earth's energy to break down rocks every year for us to use those metals from the ores. So that is why recycling is so important. So we actually have a professor up at the University of Utah that's working on extracting and recycling metals that have already been used. So right here I have a piece of a car that has been shredded up, and it is going to be getting recycled. So you can see there's copper, there's steel, there's aluminum, there's a lot of different types of metals, and there's actually even plastics, and I think there's a wood chip that accidentally got in there. So people are a lot more likely to recycle if they can throw everything into one container. I know where I live, we put it all in a blue container. So we have our plastics, we have our papers, we have our metals, all of them go into one container. Now, can anybody guess how we would separate those metals so that I could get just copper or just steel or just aluminum or just one type of metal? You can pause the video. That's right, magnets. So not all metals are magnetic. However, a lot of the ones that we use are. If any of you guys have seen Toy Story 3, we've got Woody and Buzz that are just about to go to the crusher during the when they're at the dump and they're having to get recycled. And they grab onto a piece of metal and then they get lifted up. Now, because of neodymium magnets, which neodymium magnets are actually one of the strongest magnets in the world, they didn't end up getting crushed. So that's the same as different types of metals. So we actually have a professor at the University of Utah that's working on extracting, well, on recycling these metals. So he has this machine that you can put recycled metal in, and then you can get about a 60% pure metal concentration the first run through the machine. As you run it through more and more times, it gets more and more pure, and you can get about the same concentration as what you can at a mine, except for it's a lot better for the environment because it's already been mined and it can be used again. So now let's talk about the second type of metallurgist. So we have physical metallurgists. As I said, my brother is a rocket scientist, so he works with physical metallurgy and alloy design. Now, can anybody tell me what an alloy is? You can pause the video. That's right. So an alloy is a mix of two elements or more on the periodic table, where one is a metal and the other can be a metal, or the other few can be a metal, or it can be non-metals. So can anybody give me an example of an alloy? So you may have said nitinol or brass or bronze. Those are great examples of metal-metal alloys. Now can anybody give me an example of a metal-non-metal alloy? Steel is very common. Oh, sorry, so you could have paused there, but anyways. So steel is a very common metal-non-metal alloy, and that is with iron that is a metal and carbon that is not a metal. Now we're going to talk about one of my favorites, and that's called nitinol. So you can Well, I'll have your teacher go to this little link on the top of this screen and you'll learn about nickel and titanium. So you can pause this video and go to the other one, and I'll see you soon. So welcome back. It's so great to see you guys again, and I hope you really enjoyed the Nitinol video. Now, can anybody tell me, I've got these different prizes, like I told you in the beginning, that you're welcome to choose from if you answer the questions. Can anybody tell me one of the metals that makes up Nitinol? You can pause the video. Can anybody tell me what the other one is? You can pause the video again. Great. And from the video, you might have learned that metals are made up of something, and a lot of different things are made out of this same something. Well, everything is made out of this same something. You can pause the video. Well, that would be atoms. And in Nitinol, we can actually change the phase structure and the crystal structure of the atoms. So they can go from martensite to austenite, depending on what temperature they're at. Can anybody raise their hand and tell me what an example of Nitinol would be? So you can pause the video. So we've got eyeglasses, we've got panels on the Mars rovers, we even have them in our bras, in our stints for cardiology, our braces. Nitinol is in a lot of different places. I thought it was pretty interesting that Nitinol was actually found by a man by the name of Dr. William J. Bueller in 1959 at the Naval Ordnance Lab, and he was studying the Polaris missile. He needed something to go in the nose cones in the top of the missiles. So that's how Nitinol was even found. We also are working on the wheels on the Mars rover. They can design the wheels here on Earth, and then once they get shipped to Mars, and so then they can compact them and make them small. Once they get to Mars, they'll actually pop back up into the shape that we designed them into because of the heat from the sun. So Nitinol is pretty amazing, I think. Now, there are a lot of job opportunities for metallurgical engineers. One of them is for electronics. We use metallurgical engineers a lot in cell phones and computers. So those screens actually have small amounts of metal in them. And one of our professors up at the University of Utah actually worked on designing the screen for a cell phone and a smartphone. All those ones that you put away in the beginning of class, they all were helped to be designed by one of our professors, which is pretty cool. We also use metallurgical engineers in transportation. Tesla's electric cars actually have more copper than the majority of other vehicles. And by using metallurgical engineers, we can have new alloys and different materials to improve technology. As I said earlier, my brother is a rocket scientist, so he works on alloy design for rockets. And then we can also use it in public transportation to help make it be more affordable for the government or city paying for that public transportation. We use metallurgical engineers in energy storage. We have a professor up at the University of Utah that actually works with rechargeable lithium batteries. So he works with applying different materials, different alloys to improve lithium batteries' longevity and seeing if maybe one day we'll be able to get a cell phone that lasts for, I don't know, several days rather than just a day's charge. So it's pretty amazing that by using different alloys, using different materials, we can improve our technology and our world. We also use them in alternative energy. So I brought up neodymium magnets a little bit earlier with the cell phones and the vibration option. We also use neodymium magnets for wind turbines. So the energy that it's used from, that's generated from wind turbines is usually from a neodymium magnet. We also have solar panels and hydroelectric dams. All of those have a lot of different types of metals and different materials that we'll apply a metallurgical engineer for. We can hire a metallurgical engineer for chemical plants. So in the refineries up in North Salt Lake near Bountiful, there are a bunch of different chemical reactions happening inside of those refineries to purify those materials. Now, a metallurgical engineer could be hired to come in, see what type of metal would be the best for the walls and the outer shells of those refineries to make sure that they don't corrode and they don't degrade. We definitely don't want a chemical reaction happening with the metal if we are purifying something else to refine it. We also use metallurgical engineers in biomedical devices. So right here, I have a hip prosthetic. So it was made out of cobalt. Now there are 3 different types of metals that we'll generally use for a prosthetic or a biomedical device. And those are cobalt, stainless steel, and titanium. Now stainless steel is generally used for a prosthetic that is temporary, whereas the cobalt and titanium are more for longer term. Now this prosthetic specifically, when it was at its molten stage, which can anybody tell me what molten means? Go ahead and pause the video. That's right. So molten is when metal is at its liquid phase. And so when it was at its liquid phase or molten stage, it was actually infused with diamond dust. Well, and then it was super saturated with carbon. As carbon ages, it turns more like a diamond. So those carbon atoms were able to go and attach onto the diamond particles, and then they were able to create a diamond-like structure throughout the prosthetic to make it nearly unbreakable. We also use metallurgical engineers in pacemakers and different biomedical devices, not just for hips. We also use it for ankles, arms, fingers, etc. Anywhere that you would use a prosthetic, you could hire a metallurgical engineer for that. We use metallurgical engineers a lot in nanomaterials. So the right top picture of this left panel are the nanomaterials within your cell phone. We also have two big projects happening up at the University of Utah. One is using nanomaterials to purify water and remove those heavy metal pollutants. And then the other one is working with tuberculosis sensors. So a patient can simply just breathe on the apparatus, and then they'll receive results whether that patient has tuberculosis within a few hours. Now, before, the test process would take several days. So by being able to diagnose and see if the patient has tuberculosis, we can begin the healing process and treatment to be able to hopefully save that patient's life. Now, something that I found pretty interesting is there's actually more people that die from tuberculosis in Africa than they do of AIDS. So it's a very sad fact, but still pretty interesting that we can make such a big impact here in Utah and here in America and here in the world for others that do have tuberculosis. Our professor does go to Africa multiple times a year to deliver those sensors and to help those patients that may or may not have tuberculosis. We also use metallurgical engineers in nuclear power. Now, it's pretty common for somebody that's going to the University of Utah, being that we don't have a nuclear engineering degree program, they will minor in chemical or civil or mechanical engineering and then choose nuclear engineering as their minor. Now, you can also do that for metallurgical engineering. And like I said, I'll talk more about the scholarships, but you can choose your major to be metallurgical engineering, your minor to be nuclear engineering, and then you can also choose an emphasis in nuclear engineering. And you can become trained in our nuclear reactor up at the University of Utah. And then, of course, with metallurgical engineering, we do have extracting uranium. So there's a lot of opportunity for nuclear power as well. Something that's pretty commonly known for engineers is we have a pretty high salary for our starting salaries. Here is the national average starting salaries. The top line is humanities and social sciences. For those in the back that you might not be able to see it. Then we have math and sciences, business, engineering, and computer science. And then the green bar on the very bottom is metallurgical and material engineering. Now on the right side of the screen, you can see the average starting salary if you were to decide to pursue a higher education past just bachelor's degree. So you'd have a bachelor's degree that's a 4-year degree, a master's degree that's a 6-year degree, and then a PhD that's around 8 years. Now, of course, you're going to have a higher salary with those. I would say the starting salary for a metallurgical engineer would be closer to around $65,000 to $75,000. On here, it's saying $65,000, but I think it's definitely higher than that. But that's my opinion just from my experience. Here's a potential career track. So this would be a high school graduate in the blue, and then a metallurgical engineering bachelor's degree graduate, which bachelor's, like I said, is a 4-year degree outside of college. So as you can see, you'd be hired as an engineer, then promoted to a plant engineer, a senior engineer, chief engineer, plant manager, and then the director or vice president of the company. Now that's also compared to the high school graduate, which you can see the salaries are definitely going to be different. After a 20-year salary as a metallurgical engineer, you're going to be making close to $200,000 per year, whereas a high school is quite a bit lower. However, both careers do have different salaries, and you are making money, but one life is going to be definitely a lot more effort to build a lifestyle and life salary. So my dad used to say when I was younger that if you were to pursue a high school education, get your diploma, your options are about this big. You still have options, still have opportunities. However, if you were to graduate and go to university, your options and your opportunities are quite a bit larger, and you have a lot more doors open. Now, in my opinion, it's a lot better to have more doors open than less. If you're able to go and set aside the 4 years, do it right now when you're not settled down to a family or a career, it's going to be a lot easier to get that out of the way than if you were to do that 20 years from now when you are depending on a higher salary. So So why the University of Utah? A big perk is it's close to home, so you can probably keep living where you're living now. I was fortunate enough to live with my parents during my undergraduate, and because of the U card that they offer up at the University of Utah for being a student, you receive an unlimited use of the UTA bus and UTA Trax pass. So I actually was able to just go and hop on the Daybreak Trax train and then take it to the University Stadium stop. Now that's about a 50-minute ride, and it's pretty comparable to traffic, especially when you're having to fight for parking up there. Like many schools, they do sell more permits than there are parking available, so you're going to have to kind of compete for the parking, and that can get pretty difficult some mornings. Another big perk is we have a lot of outdoor activities. So we have trails, we have biking, we have hiking, and we even have the MUS. So you can get a $50 season pass if you are a student at the University of Utah for all of the games up at the University of Utah that are home games. Now, when I went, they actually had a special through the University Credit Union that if you signed up for a savings account and were a university student, you'd actually receive a free MUS pass. So that's what I did one of the years. It was a nice little combo to get a break from my engineering nerd life to have a bit more of a social life. So it was a good little break. We also have really great academics. So we're one of the top 100 universities in the U.S., and we're ranked 40th for research in the U.S. Now, something about metallurgical engineering specifically is we're actually the second most funded research up at the University of Utah. So we're just second to pharmacy. So we've got quite a bit of research opportunities and research funding for you to become involved in. A big consideration I had to make for whether I wanted to go to in-state or out-of-state college was finances. Now, in-state tuition is going to be close to $8,000 per year. Now, out-of-state is going to be closer to $25,000 per year. So for a bachelor's degree, you're looking around $24,000 versus around $100,000 for out-of-state. Now, that's quite a bit of money. Even for in-state, that's a lot of tuition. Now, I didn't have that much saved up. I really didn't want to have to use my hard-earned savings, and I really didn't want to go get student loans. So I opted for the scholarship route. As I mentioned earlier, there's a different hierarchy system within the university. And so you have the university, the college, the department, and the degree. And all of those have different scholarships. Now, the university level scholarships are definitely the most difficult to receive. I know there's the trustees and the honors of entrance, but I know there's other ones. I received the trustees scholarship, and I'm very grateful for it. However, I still had a lot left over of my tuition due, and because of my department and my degree and my college scholarships, I was able to fund the rest of my scholarship, or the rest of my tuition. There are also need-based scholarships, so those are things like FAFSA. If you go on to Google and just Google FAFSA, it will take you to the website, and I would highly recommend applying for that sooner than later. Once the funding is out, they won't be receiving more until the upcoming year. So if you apply sooner, you're going to more than likely get more money from the government than if you wait to apply. You can apply for the university scholarships at financialaid.utah.edu. As I've been talking about, there's a lot of other scholarships for metallurgical engineering. So we typically have around $100,000 of scholarships per year to give out to students. Most students with a 3.0 GPA will receive around $1,000 to $5,000 if you major in metallurgical engineering. Now, like I said, if you're maybe interested in engineering or a STEM field and you might not know exactly what kind you're wanting to go into, I'd recommend trying metallurgical engineering. You're going to be taking the same classes as other types of engineers, so you'll be going hand in hand with mechanical engineers, civil engineers, med students, chemical engineers. They're all going to be taking the same courses until about your junior to senior year. So you can try metallurgical engineering, get it paid for, get your tuition paid for, and then see if it's for you. It ended up being for me, and I really enjoy it now. You can apply for our scholarships at msc.utah.edu. On the back of the knit and all wires is our website, so it's in bold right on the back. If you are interested, there's going to be some more questions at the end of this presentation, so definitely keep participating, and thank you guys so much for your attention. So why the University of Utah? We have a great department. I absolutely love our department. It's very much like a family away from family. So I love the secretaries, the professors, my peers. They are just wonderful. So one big perk is we have really small class sizes. Now the PowerPoint's saying it's around 10 to 30 students. I don't think in my department I had a larger than a 15 student class. They're pretty small classes, and because of that, you're able to get to know your professors a lot better. Now in some of the upper division or the other departments and even the higher upper division classes, so like my physical chemistry, which is quantum chemistry, had a lot of students, and my teacher didn't even know my name. It's pretty common that in those larger departments, the teacher or the professor will give the presentation and the lecture, and he'll probably have office hours for a few hours, he or she, and it can be pretty difficult to schedule and get to know your professor, especially if you're struggling on the concepts in those classes. Whereas with metallurgical engineering, the teachers are very, very open. They're more than willing to come in, schedule a time that you could work with them, and you can express your concerns that maybe you're struggling with a concept or not quite getting something, or you didn't do well on a test. They'll work with you. I like to say that it's pretty difficult to fail in metallurgical engineering. If you're showing up, you're trying, you're giving effort, you're trying your hardest, you're going to do well. And metallurgical engineering, like I said, it's like a family away from a family. It's really nice. Since I graduated, they actually are now offering emphases. So they have degree emphases. They have physical metallurgy, particle and mineral processing, nuclear, biomedical devices and sensors, energy conversion and storage, and chemical processing. So as I said, they didn't have that when I graduated, but now they are offering that. So that's kind of when you graduate, you're going to get your diploma. It's kind of like a gold star on your diploma. So it will give you a bit of more of a oomph for when you apply for your different different careers, or if you decide to go out of state to pursue a higher education. And a big perk of the University of Utah is it's nearly 100% job placement, and those are at the salaries that I was talking about earlier, around $70,000 to $75,000. I would say is the starting salary for a bachelor's degree. So that's a huge perk. And then we also have a lot of opportunities to get involved at the University of Utah. On the right side of the screen, you can see two of my friends. So that's Alex and Alec in the middle, and then one of our professors, Krista Carlson. They work with nanomaterials and aerogels. Luckily, I was able to work with different research projects in my undergraduate as well. I wasn't on Alex's team. However, I did work with a professor by the name of Dr. Michael Free. I worked with rare earth element extraction and copper extraction, and I really enjoyed being able to have that hands-on experience during my undergraduate. Now, it's not so common in other Utah schools and out-of-state schools especially to be able to get so much hands-on experience and actually be published in different research articles and research magazines for your research just as an undergraduate. And a big perk is they're paid positions. So you can join the workforce and already have experience under your belt. Like when I applied for Freeport-McMoRan, I actually had 3.5 years of experience already under my resume to apply for my career. We also have different clubs. So we have bladesmithing, the material bowl, nuclear material management. Here on the bottom, you can see our two material bowl winners. So that's the 2011 and the 2016 team. So the material bowl is kind of like a Jeopardy style game where you're able to go and answer different questions about metallurgical engineering and material engineering, and you can win different awards, different scholarships. And then we also have bladesmithing. So they have this national competition where different schools are able to go and enter a blade or a dagger or a sword into the competition, and it's judged by its different physical and just its design, so its physical aspects and its design. We also have SWE. So I was part of the SWE. It's the Society of Women Engineering. So it's not just for women, it's also men are more than welcome to come. They have a lot of different outreach opportunities. So they actually have a Girl Scout night where a bunch of elementary aged Girl Scouts are able to come up to the University of Utah, and we teach them about STEM. So STEM is science, technology, engineering, and mathematics. And we do little science fair projects, and it's a really fun event. And then we have Day in the Life of an Engineer. If you guys are interested, you're more than welcome to reach out to U of U SWE, and they'll hopefully be able to get you to come and shadow an engineering student. So it's where a high school student is able to come and see what the life of an engineering student is like. So they can go to the professor's classes, they can get to know the students up there, get to know kind of the culture and the environment. And then the last part of SWE is they have something called Evening with Industry. So that's where an industrial job employer will come to this kind of, I don't know, dinner, ladies' night out. It's really fun. They're able to give you pointers on your resume on different internships that they have available for the upcoming summers. So for those of you that might not know, internships are kind of a job during the summer that you're not committed to the company, but you can kind of get a feel whether that company would be something that you would entertain once you graduate. And then they also tell you different job opportunities that will be available for their company in the next little while. So how to prepare. I think there were quite a few sophomores, quite a few juniors. So for you guys, I would highly recommend to take science and math courses. So to keep taking those. I had a lot of people in my high school class that just wanted to finish the bare minimum requirements for high school and get that box checked, and then not have to take English or science or math courses until, well, ever again, really. However, I wouldn't recommend doing that. So if you do that in your high school years, you're more than likely going to forget them by the time you get to college. Now, if you don't have scholarships, you're going to have to pay that out of pocket to remember and remind your mind what you learned in high school or forgot that you learned. And if you do have scholarships, it's going to take you longer to have to take those classes once you get to the University of Utah. I would recommend taking as many math and science AP and concurrent enrollment courses as you can, and not just math and science, but really any of them. I took as many concurrent enrollment courses as Riverton High School would allow. That's where I went to high school. And then I was also able to self-study for some AP classes that wouldn't fit into my course schedule. So I self-studied for AP Spanish and AP Photo. And so AP Photo, I was just able to go and talk to the photo teacher, and she was able to help me with my photos, helping me with Photoshop, and then sending in my photo prints with her class. So it was pretty nice, and I didn't have to have that be one of my classes in high school. I would also recommend to get good grades. Don't take too many of those AP and concurrent enrollment classes if it's going to plummet your GPA. Make sure that it's balanced and that you can manage it without causing extreme problems for your GPA. I would also recommend to develop good study habits. I was definitely one of the types of people that had to study every day, had to read books, had to keep refreshing myself over what subject we went over. However, my brother was very different. He would look at something and he would know it just like that, like super quick, and that was all through elementary, middle, and high schools, and part of college. So if you're like that, that's awesome. However, it might catch up to you like it did my brother, and he had to actually start setting aside time to learn how to study again. I would recommend to learn learn computer skills. So learn Excel, learn VBA, that's the kind of the coding version of Excel, learn Python, learn Java. If you can start coding now, it's going to be a lot more beneficial for you later. And check the deadlines, check admission, check for scholarships, check housing. If you have social media, I would highly recommend going and following my social media. It's at Metallurgy with Marina, and I'll be posting all the scholarship deadlines, what type of applications you can use Metallurgy for, and you can also go to our website. So it's msc.utah.edu, and those are for all of the scholarships. For my seniors that are watching this video, I would highly, highly, highly recommend applying for the scholarship as soon as you can. So again, it's msc.utah.edu, then go to undergraduate, and then under undergraduate is scholarships in full caps. You just click on it. It's a several page scholarship application, super easy, and you can still apply now. And for my juniors and sophomores, you can apply for that this upcoming December. And like I was talking about with the scholarships, you can apply for university, college, department, and degree scholarships, and you can piggyback all of them. So if you were to earn more scholarships than your tuition is due, you actually get to keep that additional money for yourself. So you can put it in the savings account, you can put it towards a new computer, you can put it towards really anything. So anyways, it's great. Okay, if you guys have any questions, please make sure to reach out to my social media at Metallurgy with Marina, or if you don't have social media, that's just fine, and just have your teacher email me the different questions that you guys do have. I do have a few different questions for you, just for if you are still wanting the prize or one of the prizes in the goodie bag or the baskets. I'll start with, what are two types of metallurgical engineering? So I said there's two kinds. There's blank and blank. So I'll go ahead and pause the video now. And so that's right, there are physical and extractive metallurgy. And then, what are the two types of extractive metallurgy? So go ahead and pause the video again. So we've got pyrometallurgy and hydrometallurgy. So pyrometallurgy has high heat, and hydrometallurgy has diluted acid and water. Next question, what percent of the Earth's energy is used for crushing? Go ahead and pause the video. That's right, it's 4%. And what percent of concentration of copper is in Bingham Canyon Mine? You can pause the video. It ranges from 0.1 to 1%. How do we recycle metals? Go ahead and pause the video. We generally use magnets and neodymium magnets. And what percent of the periodic table is made of metals? Go ahead and pause the video. It's around 75 to 80%. In the beginning of the presentation, I talked about a dagger that was made out of iron. Can anybody remember whose dagger that was? Go ahead and pause the video. It's King Tut's dagger. Good job. And can anybody tell me what is an ore? Go ahead and pause the video. It's a rock with a high concentration of metal. So great job for whoever answered that. And can anybody tell me what my website is? You can go ahead and pause the video. msc.utah.edu. Perfect. And then the last one, what is my social media handle? It's at Metallurgy with Marina. So again, if you guys have any questions, please make sure to reach out to my social media, or like I said, you can have your teacher email me any questions. I hope you enjoyed this video and this presentation, and thank you so much again for your participation and for paying attention. Thank you so much and have a great day.